Hello class, and welcome to this video lecture on acids and bases, buffers part 2. Okay, so in a previous video lecture, we talked about the definition of a buffer. A buffer solution consists of a weak acid and its conjugate base present in significant amounts. Okay, so let's suppose that we have 0.10 moles per liter of HA and 0.10 moles per liter of the sodium salt of the acid, and we place these components in water to obtain a solution. So we're going to have primarily three components here. We're going to have HA. This salt is going to dissociate into sodium ions and the anion of the weak acid. Okay, so we can write this equilibrium equation, the weak acid in water. Of course, that has a Ka, products over reactants, leaving out the water. Okay, now if we substitute into this equation our Ka expression, we have 0.10 moles per liter of HA, 0.10 moles per liter of the anion. Notice that those are going to cancel out, and we end up with our hydronium ion concentration being equal to the Ka. And what is the Ka? It is a constant, right? It's the acid ionization constant. So if these are equal to each other, they cancel out, and our hydronium ion concentration is equal to a constant, right? The acid ionization constant. If we take the negative log of both sides of that equation, we get the pH being equal to the pKa. Okay, so what is really critical, class, in a buffer solution? What is really critical is this ratio right here. The ratio of the conjugate base of the weak acid to the weak acid. Okay, now if this ratio is equal to 1, we have what is called an optimal buffer. Okay, how is this going to be equal to 1? If this concentration is equal to this concentration, if the two concentrations are equal, okay, what's going to happen? They're going to cancel out. We're going to get the hydronium equal to Ka and the pH equal to the pKa. That's what we have with what we call an optimal buffer. Okay, it's called an optimal buffer because it can neutralize just as much added acid as added base. Okay, it can neutralize just as much added acid as added base. Now, technically, class, for a solution to be classified as a buffer, this ratio, it doesn't have to be 1, but it needs to be between 0.1 and 10. This ratio needs to fall in the range between 0.1 and 10, strictly speaking, for it to be considered a buffer. If this ratio falls outside 0.1 to 10, technically it's not really a buffer. Okay, it's not really a buffer. All right. Now, let's explore some more aspects here of buffers. Okay, so we've got our weak acid, the conjugate base. There's going to be some ion. It doesn't have to be the sodium ion. It could be the potassium ion or some other group 1A or 2A ion. All right. So let's suppose that we have solution 1, a weak acid and its conjugate base in the form of a salt, equal concentrations. That would be an optimal buffer, wouldn't it? Okay. This is what we had on the previous slide. We had the weak acid and its conjugate base present in what? Equal concentrations. That's a buffer, an optimal buffer. Look at solution number 3, okay? This is an optimal buffer also, okay? The same two components, they're present at the same concentrations, okay? So we've got 3 solutions class, that are optimal buffers. Okay? Now, when we talk about the buffer capacity refers to the amount of acid or base that can be added to a given volume of a buffer solution before its pH changes significantly, usually by 1 pH unit. Okay? So the buffer capacity refers to how much acid or base can be added to the buffer before the pH changes. Now, class, this solution right here, of these three solutions, they're all optimal buffers. This is a better buffer than this because this is 10 times as concentrated. This can neutralize much more acid or base compared to this. Okay? This, of all three buffers, this would be really kind of the worst one in terms of the amount of added acid or base it could neutralize. This is 100 times less concentrated than this. So when we talk about buffer capacity, solution number one has the highest buffer capacity. It's the most concentrated. It's going to be able to neutralize much more added acid or base. This solution has the lowest buffer capacity. Okay? So something that's really important to remember, in terms of buffers, the higher the concentrations of the buffer components, the better. Okay? We always need to remember that this ratio needs to be between 0.1 and 10, strictly speaking, for it to be considered a buffer. Okay? And if this ratio is equal to 1, we call that an optimal buffer. Okay, so some important points to remember about buffers. Okay, let's look at identifying buffers. Okay, let's look at some example problems here and let's see if we can identify some buffers. Which of the following combinations could make a buffer solution? Okay, so we're going to look at some different scenarios here. Okay, some HF combined with sodium fluoride, some hydrobromic acid combined with potassium bromide, ammonia combined with ammonium chloride, sodium bicarbonate combined with sodium carbonate, and potassium chloride combined with potassium hydroxide. Which of the following combinations could make a buffer solution? All right, let's consider number one. Okay, so remember, what is a buffer made of? A weak acid and its conjugate base. Okay, what do you think about number one? Yes, this combination could make a buffer solution. We have a weak acid. This is not one of the 6 strong acids. We have a weak acid and its conjugate base. So this would make a buffer solution, this combination. Okay. What about number 2? What do you think about that? Make a prediction. No. This would not make a buffer solution. What do you have to have? A weak acid and its conjugate base. This is a strong acid. This is a strong acid and its conjugate base. This would not make a buffer solution. Okay. What about number 3? What about number 3? Look at that. Make a prediction. Do you think that that combination would make a buffer solution? Yes, it would. Do we have a weak acid? Now you look at that and you'd say, well, that's ammonia. That's a common weak base. Do we have the conjugate acid of this base present? We do. The ammonium ion is the conjugate acid of ammonia. Is the ammonium ion a strong acid? No, it's not one of the 6 strong acids. What does that mean? It must be a weak acid. So a weak acid, in terms of the ammonium ion, a weak acid and its conjugate base, that would make a buffer solution. Okay, let's look at number 4. make a prediction. What do you think about number 4? Would number 4, a combination of sodium bicarbonate and sodium carbonate, would this combination make a buffer solution? It would. Okay, now you might look at that and say, how can that be a buffer solution? We've got 2 salts. Okay, well, yes, we do. We've got 2 salts. So we put this in water, it's going to split apart into sodium ions and bicarbonate ions. When we put this in water, it's going to split apart into sodium ions and carbonate ions. Do we have a weak acid? The bicarbonate ion has a hydrogen that it can donate. So the bicarbonate ion is an acid. It's a weak acid. So we have a weak acid and its conjugate base. So yes, this combination would make a buffer solution. Okay. What about number 5? What do you predict about this combination? Potassium chloride, potassium hydroxide. Would that make a buffer solution? No. You have to have a weak acid and its conjugate base. Do we have a weak acid? No. We don't even have a weak acid here. Okay? So, remember the definition of a buffer. That way you'll be able to positively identify buffer solutions when you encounter them. Okay? Now, let's look at some more aspects here. Okay, so how are buffer solutions prepared? How are buffer solutions prepared? Well, based on what we just talked about in terms of the definition of a buffer solution, okay, let's explore this. Now, class, we're going to assume that HA is a weak acid, okay? So on this slide, we're considering HA to be a weak acid, and we're considering the anion to be the conjugate base of a weak acid, okay? So one way we could make a buffer is to dissolve enough of a weak acid and its conjugate base in water so that the ratio of the conjugate base to the weak acid is between 0.1 and 10. Okay, but there are a couple of other ways we can make buffer solutions. Add enough hydroxide ion to a solution of a weak acid until this ratio is between 0.1 and 10. Okay. Well, let's explore this. Okay, so suppose that we take a solution of a weak acid. A solution of a weak acid is not a buffer. But if we have a solution of a weak acid and we add hydroxide ion to that, what can happen as a result of that? Some of the weak acid is converted into what? The anion of the weak acid. In other words, the conjugate base of the weak acid. So if we have a solution of a weak acid, we can add some hydroxide and convert some of this into this. If we add enough of this so that we end up with a ratio of both of these between 0.1 and 10, that would give us a buffer solution. So we can do that. We can do that. Okay. There's a third way we can make a buffer solution. We can add enough hydronium to a solution of A- until this ratio is between 0.1 and 10. Okay, so let's suppose we have the conjugate base of a weak acid. We have that solution. We can add a strong acid to that and slowly convert some of this to HA. We add enough so that we get both of these chemicals, both of these species in the solution such that the ratio is between 0.1 and 10. That's possible. Okay? So the most direct way of making a buffer is number 1. That seems the most obvious, doesn't it? But we can also make buffers by adding a strong base to a solution of a weak acid, or by adding a strong acid to a solution of an anion that is the conjugate base of a weak acid. Okay, so we're going to explore these in just a few moments here. Okay, so let's look at an example problem. Buffer example problem number 1. A 5.36 gram sample of ammonium chloride was added to 25 milliliters of 1 molar sodium hydroxide, and the resulting solution diluted to 0.100 liters, 100 milliliters. What is the pH of the solution? The pKb for ammonia is 4.74. Okay, so class, this is going to utilize here some of what we talked about in the preceding slide. Okay, so let's look at this. We've got 5.36 grams of ammonium chloride. We're going to convert that from grams to moles. So we set up the molar mass. We convert that to moles of ammonium chloride, 0.100 moles of ammonium chloride. Okay. We're going to divide that by 0.100 liters. We basically have a 1 molar solution of ammonium chloride. Now, we've got 25 milliliters of 1 molar sodium hydroxide. Okay, so we're going to take the 25 milliliters, convert it to liters. We're going to multiply that by the molarity of the solution. The liters cancel. That would give us 0.0250 moles of sodium hydroxide. We divide that by the 0.1 liters. Okay, so that gives us 0.250 moles per liter of sodium hydroxide. Okay, so look at what we've got. Do we have a weak acid in its conjugate base? Well, this is a weak acid, but we're reacting it with a strong base. Okay, so what we're doing, class, this is the reaction that's going to occur. When we add this sample of ammonium chloride to sodium hydroxide solution, this is what's going to happen. The hydroxide is going to react with the ammonium ion. This is a weak acid. It's going to donate a proton. We're going to get water and ammonia. Okay, so we're going to make kind of a modified ice table. A modified ice table. Now, water is what? It's a pure liquid, so we're not going to consider that in our table. Okay, now we're plugging molarity into this. Okay, so our initial molarity of the ammonium ion is 1 moles per liter. 1 mole per liter, I guess I should say. We don't have any ammonia to start with. We're adding 0.250 moles per liter of hydroxide. Okay, so what's the change going to be? Okay, well, we're going to have minus 0.250 for the hydroxide. What would we have here? We've got a 1-to-1 mole ratio, so that's also going to be minus 0.25. What are we going to have over here for the change? Plus 0.250. Okay, so at equilibrium, we're going to say approximately 0. Remember, hydroxide can never be 0. But in my table, it comes out to 0. I'm going to say approximately 0. It's going to be small. Okay, the ammonium ion is going to be 0.75, and ammonia is going to be 0.250. Okay, so what we can do, we can plug these values into the Ka of the ammonium ion. Okay, so look at what happens, class. This is what we were talking about before. Here we have a solution of a weak acid. We're adding hydroxide, forming ammonia. And when we do that, what do we end up with? We end up with some of a weak acid and some of the conjugate base is the ratio of this to this, is the ratio of this to this between 0.1 and 10? It is. If you check it, it certainly is. Okay. Now, we could, if you try to look up the Ka of the ammonium ion, you're not going to find it in your book. We are given the pKb for ammonia, so we can calculate the pKa. The pKa for the ammonium ion is going to be 9.26. We want the Ka, so we take 10 to the negative 9.26. We get a Ka of 5.5 times 10 to the minus 10. Now we simply substitute in these values into our Ka expression. We solve for the hydronium ion concentration. We want the pH, right? So we take the negative log of both sides. We get a pH of 8.77. 8.77. So class, this is an example of a buffer solution. We did not take a weak acid and its conjugate base and dissolve them in water. We took the solution of a weak acid, or say the solution of a weak acid. We actually took a solution of a base and we added a weak acid to it, right? And they reacted with each other such that we ended up with the ratio. Remember, this ratio right here, class, is what's important, okay? This ratio right here of these two, okay? So this is how you solve a problem like that. So you can generate a buffer through a chemical reaction, okay? Let's look at another example. Buffer example problem 2. 47.3 grams of potassium phosphate and 72.5 grams of potassium hydrogen phosphate is dissolved in enough water to make 1.5 liters of solution. Calculate the pH of the solution. Okay. All right, so look at what we've got. Do we have a weak acid and its conjugate base? We do. The weak acid is right here. These are both salts. Okay, but this salt does have a weak acid component, doesn't it? So this is a weak acid. The phosphate ion is the conjugate base. So yes, we do have that. Okay, so we take the 47.3 grams of potassium phosphate. We use the molar mass of potassium phosphate. The grams cancel. We get the moles of potassium phosphate. We take that and divide by the 1.5 liters. Okay, so we have a 0.15 molar potassium phosphate solution. Now we're going to take the mass of the potassium hydrogen phosphate, okay, divide by the molar mass here. The grams cancel. We've got 0.416 moles of potassium hydrogen phosphate. We take that, divide by the 1.5 liters. Okay, we get 0.28 moles per liter. All right, so we set up our Ka expression. Okay, now I looked that up in the appendix in the textbook. Okay, it wasn't given in the problem here. I had to look it up. Now, class, you will have access to either a Ka table. You'll have access to that, or it'll be given in the problem. Here, you had to, resort to your book, to looking it up. We don't memorize these, okay? We look them up. All right, so we substitute for the phosphate ion. We got 0.15. For the hydrogen phosphate ion, we've got 0.28. We solve for the hydronium ion concentration. We take the negative log of both sides. We get a pH of 12.11. So this is a basic solution. Okay, so class, this problem here involves what? Simply taking a weak acid in the form of a salt, taking its conjugate base in the form of a salt, and dissolving both of those into a solution. And you can see, class, this ratio does fall between 0.1 and 10. So class, I hope that you have found this video lecture helpful in your understanding of buffers.